Elizabeth challenged me with not showing a bunch of data. So where do you go when you don't want to show a bunch of data? You go to your notes from class. So we're gonna get a little bit of experience with the poor kids at Iowa State who have to pay to see this get, and then we'll bring it back in, bring in the CABBI. So I think everyone's aware from implications from all the discussion we've had that we want to find the places to produce bioenergy that aren't going to compete with food crops, or at least have minimal competition. But I wanted to take a step back and think a little bit more globally about where this paradigm came from in the first place. So you don't need to make out the details of these two maps, but you just need to look at the comparison of them two. The one on the bottom is where we are currently growing crops, primarily food crops, of course, places where there's lots of rain, deep soils, and relatively flat terrain. And then you have the map above, which is basically one minus the map below. That's everywhere else. And so what's primarily in the map above is where plants can grow, but not where we can harvest them very well. Those are trees, okay? So you'll see some big white spots missing on the map on the bottom, and that's either places where there's lots of trees that have lots of carbon in them and lots of nutrients in their soil and lots of beautiful different types of plants, or there's lots of deserts, okay? So when we're trying to figure out where we're going to put these things, when you take a step back from the global perspective, there's actually not big chunks of land just waiting to grow these crops. So we need to think about getting pretty precise about where we're going to target these things. And the same location that's a good spot for one feedstock, or even the same region, but especially the same location, is not going to be the same, not going to be the best across the portfolio, even though they're pretty related, as Steve Long elegantly pointed out. They're going to perform differently across even pretty close spatial scales. So the sustainability team, the way they figure out the location we should do this is primarily through trying to increase the services that the ecosystem provide. So for those of you who don't come from this world, we use this term all the time, ecosystem service. It was generated before the Millennium Ecosystem Assessment, but it was really solidified as a paradigm in the community about 15 years ago through the output of this document. And it's the foundation for most of the way that we kind of try to frame things up. So I just went ahead and went with the gory definition down below. But the idea is the ecosystem service is what we get back out of an ecosystem. And that can be lots of different things. They break them down into into categories that sound a little nebulous at first until you see the lists that go along with them. So the first one, the most intuitive one, would be an ecosystem service of provisioning. What do we get? What do we get directly, tangibly usable out of these ecosystems? So we want to get the most food, of course, that we can, and we want to get water out of it that we can actually still use and still drink and still swim in. We don't eat the timber, it tastes terrible, but we can make lots of useful things out of it. And then we've just seen all the wonderful uses that we can do with the other parts of the plant that aren't necessarily edible or you can't make into a table. We can also think about these ecosystems as regulators. If the plants weren't going where they are, the climate that's going on around them would be much different. For anyone who's ever spent 24 hours in a desert, I haven't because I like the temperate zone, you would notice that the daytime temperature is a lot different than the nighttime temperature. And that has a lot to do with the plants that are growing there. The plants themselves actually regulate the climate that are going on by changing the phase of water during the day and actually reflecting radiation differently than a desert would. It causes rainfall, it causes shadowing, it causes the entire climate to be impacted. So what we do on the land surface actually affects the climate that's growing above it, especially if you're talking about large regions like the Corn Belt in the US and Brazilian agriculture in the Southern Hemisphere. Let us not forget, although CABBI doesn't spend a lot of time on these recreational uses, although Tom Clemente was really pushing on the idea of getting hemp into our portfolio, there are recreational uses, and Illinois just joined the group of 11 on that. There are recreational uses for our ecosystems, and so the ones that the Millennium Ecosystem Services, the Millennium Ecosystem Assessment will list are things like habitats for animals that we can either look at or shoot at. We could also just get spiritual benefits from looking at beautiful places. CABBI is not quite that deep into the portfolio, but let's not forget that these things are also giving us benefits in the feeler. Okay, so they're really important. They're really important, and what we have out there, we went ahead and took about 30% of what was growing these natural ecosystem services out of those natural unmanaged situation over the last 10,000 years, primarily over the last 100 years or so. But I want to take a second to think about how much ice-free land there really is for each person on Earth. So our current population is around 7.6 billion. I didn't look at the ticker this morning, but that's a good rough number. If you take out the 200 or so, or 20 or so million square kilometers that are under ice, you're left with about 130 million square kilometers of land on the face of the Earth. If you take that top number divided by the bottom number, you end up with about 0.2 square kilometers per person, which even for us metric nerds in the room, that's kind of a weird thing to get your head around. So that leaves 4.2 acres per person in terms of ice-free land for each one of us to deal with. Well, that seems like actually a pretty good section. That's probably about the footprint of the I-Hotel here, right? Something like that. So we should be able to eat on that. But then remember, I just showed you the output of how that doesn't actually quite work out that way. To put it in terms of Iowa State terminology, we have it would be about 3 of our football fields, and actually University of Illinois' football field is just the same, although it takes them a little bit longer to get across it. And I'm sure it's some number of soccer fields, but I didn't want to go on that part of the internet to figure out how big that would be. All right, so, but remember, only about 11 or 12% of that land have we actually coaxed into making things that we can eat. So when you take those fields and divide it out, you're only left with about half an acre per person for today's population and today's climate scenario that we're looking at. Double that again is used for grazed pastures. And so all these lands are providing ecosystem services. We're much more closely tied to this half acre and the whole acre below. But we don't want to mess with those too much. We want to make them better if we can. And in fact, there's some things happening, especially on this half an acre per person, that we could actually avoid quite a bit with some of the feedstocks that CABBI is interested in. Okay, the population of the Earth is not static. Here's a cool picture from the internet of a bunch of people on a train. I don't know if it was moving anytime recently or how they all got there, but it looks like it's pretty crowded. So the population of the Earth is growing somewhere between 1 and 2% per year. That's 70 new million people per year. And if you extrapolate that down to an hour, which is how long one of my class periods are, and remember this is where these notes are. Luckily, you guys only have to take 10 minutes. You get 10,000 new people joining us on Earth every hour. So that means that taking that growth rate, we lose approximately 1 Post-it note's worth of land per person during the time of one lecture that I would deliver. You guys are only getting 1/5 of a Post-it note lost today. And that puts it into pretty tangible terms. You think about the football field, and you think about it covered in Post-it notes, and every hour someone's going out and pulling off one of the Post-it notes, and you can't deal with that one anymore because we have more people, okay? So we have to get pretty darn strategic about this if we want to really shift the paradigm and do some other things on the landscape. We've got some really cool stuff to do it with, and some stuff that's really productive, and it can be pretty good for the environment. So CABBI has this portfolio that kind of goes all the way from the economics that Madi will talk quite a bit more about, to surveying all this land with a much more fine-tooth comb than those blurry maps that I pulled out of the Millennium Ecosystem Assessment, and thinking about the cycling within those locations across that landscape. That's how we cover this full environmental spectrum. I wanted to focus on one, it's a pet of mine, and I think it's a good example, and get a little bit more specific about it as well. So water quality is one of these key examples that people in the sustainability theme are working on. For those of you who aren't familiar, each year we dump about 1 million metric tons of reactive nitrogen into the Gulf of Mexico. Most of that comes from Iowa and Illinois, and that causes an area of no oxygen where the things that used to live there don't have a good time, but we think we can do better at CABBI. So the idea is this. Not only do we apply fertilizer, which you've heard a lot about, we want to manage that well because we have to pay for it, but also these systems are producing a lot of fertility on their own. This is why when DK Lee shows a graph of little fertilizer response, this is what's going on. It's not that the plants don't want to have any more nitrogen, it's that the soils have a lot of them in the first place. So here we have a time series of the production of nitrogen that plants can use by the microbes that we're studying so much in CABBI, and then we have the timing that a corn plant would take it up. And anytime you have a mismatch and you couple that with water moving through the system, that water is going to make its way to the Gulf of Mexico, and it's going to cause unhappiness down there. So the idea of a perennial crop is to shift this a little bit. You don't have to wait until the flooding has stopped to plant it. It'll be there and growing and ready to go as soon as it gets warm enough. And also maybe, if you can get a really high yielding one, that curve shifted up a little bit, you could also take up basically synchronizing the entire mass of available fertilizer, minimizing how much we have to put in and maximizing the retention of that inside the system. So this is why we keep talking about miscanthus. Not only from its photosynthetic capacity and all the other cool traits, but also because it's really good actually at doing this, and Evan alluded to that earlier. So sorghum would look probably a lot more similar to corn here, but it does potentially have a little bit less inputs in terms of fertilizer. You can see this is the fertilizer we're losing down below ground, or the nitrogen we're losing down below ground, but also above ground losses turn into nitrous oxide, which really has a big climate impact. So we want to avoid both of those in CABBI. So I wanted to hone in on kind of one specific example and be a little bit less nebulous about how CABBI is thinking about this. Really, it only comes down to about 4 or 5 things we really care about: nitrate leaching, N2O emissions, soil carbon, holding on to the soil, and yield. Yield. Okay, so to do that, these things can't happen in isolation. How much time do I have? All right. So it requires a flow chart. And you've seen this diagram already. We're all working really hard together on this. We need to know what to grow where and what it's going to impact, how it's going to impact the environment. And we want to do better than what agriculture has done over the past 100 years. All right, thank you.